Hi, my name is Aparna Ayyah, and during this Datathon, I worked with Matt Hill. We are Team 77, and we decided to tackle Synchrony Financial's problem set, which dealt with equitability in relation to voice assistants and how we can improve that.
For this presentation, we have broken up our methodology into 5 different components: problem context, data sets overview, custom model performance, textual understanding, and conclusions.
To give you some context into how inequity happens with voice assistants, we have to start with the data set, which has historically been drawn from standard white American dialects. This leads to an almost 2 times higher word error rate for accented speakers versus white speakers. These two components create a positive feedback loop of sorts, which skews the future models because of the current error. Some of the key factors that can lead to voice assistants not working well for certain groups include accented speech, speech impairment, or children. And for the purposes of this datathon, we decided to focus on accented speech and how that can be improved.
As you can see below on the left side, we have the composition of the Common Voice dataset. As you can see, the US composes 82.2% of the dataset, whereas on the right side, we can see the composition of English speakers worldwide, in that the US only corresponds to 22.8% of English speakers worldwide. This illustrates the problem with the training data in that it's not very representative of English-speaking users all over the world.
So the voice assistant sequence from the speech input to the action can be broken up into 2 big chunks. The first being transcribing that speech into text, which is speech to text, and then turning that text into understanding, which is the text to understanding part. We have illustrated all of the potential improvements that we see in white, and we will take you through those for the rest of the presentation.
In terms of improvements in speech to text, we observed 2 different data sets. Our first being the INDIC TTS dataset, which is an open source speech dataset created by the Indian government. We use this dataset to create our custom model. We also looked at the Common Voice dataset, which is another open source speech dataset created by Mozilla. We chose to use this dataset because it's the closest we could get to proprietary datasets, such as the ones used by Google and Amazon. It should also be noted that the Common Voice dataset was used to train the deep speech speech recognition software.
So in order to train our custom model, we started off with WAV files that are drawn from the INDIC TTS Indian Accents database. After that, we turn these WAV files into spectrograms, which allows us to see the audio files in terms of a graphical input. And then we normalize these and then ran them through a recurrent neural network, which is, we selected this because it's the best for sequential data, which is what speech data is. After this, we ran our model through a time distributed layer to produce our final trained model. Now to see how our trained custom model performs in comparison to the generic deep speech model, we can see that over 20 epochs, the word error rate for our custom model was only about 16%, whereas the word error rate for the generic model was 44%. In addition, the word accuracy rate was about 30% higher for our trained custom model in comparison to the generic model. To the right, you can see that the prediction confidence of deep speech drastically varies when you take different accents. So for the British and American accents, it was above 90%, which is pretty good. For the Indian accent, it was only about 64%, and then for the Bangla accent, it was about 18%. And these disparities are clearly illustrated by the composition of the training data set that we took you through earlier in the presentation. For cross-validation, we decided to use the K-fold method. Over the 20 epochs, you can see that both our validation and training loss significantly decreased, and we also did not overfit our model to the training data set.
In terms of improvements in text to action, we looked at the n-gram model. This method is used by conventional speech recognition models. The way it works is it calculates the probability of the next word given the past n-1 words. For your standard commercial speech recognition softwares, such as Alexa, which have an n equals 4, the advantage of using the n-gram model is that it uses some context in terms of prediction. So it'll keep track of the past n-1 words, but its limitations are that it does not keep in mind longer range dependencies.
So we're suggesting that the conventional n-gram model be supplemented with a neural model and noise contrastive estimation as well. So the step 1 of our suggested model sequence would be to run the conventional n-gram method and then go on to refine that using a neural model. And the reason for using a neural model is because it's a lot better at recognizing those longer range dependencies. And then step 3 is to use a noise contrastive estimation. So steps 1 through 3 combined actually reduce the word error rate by 6.2%, which is a significant improvement. However, this does increase the computing time. So then in order to mitigate that increase in computing time, we suggest using quantization methods so that the net increase in computing time is just milliseconds.
As far as additional improvements, we suggest setting a context. So for commercial phone lines, it will prompt the user a certain keyword for a certain service. And we think that it would be a good idea that the Alexa or speech recognition software would respond to some context, such as temperature, and then it would be followed by some temperature-related command. This would add time to the usage of the speech recognition software, but it will also drastically increase the accuracy. We also suggest the utilization of repetition, in that if the speech recognition software is not confident enough in what the user said, it will ask the user to repeat themselves and use that data for future reference to increase customer satisfaction in the long term.
In conclusion, the speech-to-text component of the voice assistant can be improved by having a more robust training dataset because the current datasets are not accounting for natural variations like accents. And then we also have proven that mirroring population composition with the training data drastically improves model performance. As you saw, our Indian accent trained model performed much, much better than the generic deep speech model. And we think this could be implemented in a business sense by allowing the user to input the preferred model, perhaps via a select dialect option. And we believe that the text to action component of the voice assistant can be improved by implementing the n-gram method along with the neural model to better understand long range context. And then also by allowing the user to set the context so that misunderstandings can be avoided in relation to word or phrase choice.
That's all for our presentation. We'd like to thank you for watching and hope you all have a great day.